A single data center drinks 5 million gallons of water a day, roughly the same amount a city of 50,000 people would use, and almost none of that water ever comes back. It boils off into the sky. That fact alone should bother you because you probably think of data centers as electrical machines, boxes of silicon and wire that consume electricity and produce heat. That's true, but it's incomplete. The missing piece is water. And once you see why water is involved, the entire cooling architecture of the modern internet starts to make sense. Let's start with what's actually happening inside one of these buildings. A data center is a warehouse packed with tens of thousands of servers, each one a computer running continuously, every second of every day, processing requests, storing files, running the algorithms that recommend your next video. Each server generates heat, not as a side effect, but as an unavoidable law of physics. Every watt of electricity that goes into a processor eventually leaves as heat. There is no way around this. A single rack of servers can generate as much heat as several space heaters running nonstop. Now multiply that by thousands of racks in one building. The interesting part is what happens when you concentrate that much heat into an enclosed space. Air alone cannot carry it away fast enough. If you tried to cool a modern data center with fans and air conditioning alone, the servers in the center of the room would cook themselves within minutes because air is a poor conductor of thermal energy. It simply cannot absorb and carry heat quickly enough to keep pace with the load. This is the problem that water solves, and the reason engineers reach for water isn't tradition or convenience. It's a property of the molecule itself. Water can absorb roughly 4 times more heat per unit of mass than air can, for the same rise in temperature. That difference sounds modest, but at data center scale, it becomes the entire design philosophy. Engineers pump water through cooling loops that pass directly behind server racks, absorbing heat at the source before it ever spreads into the room. That heated water then travels to external cooling towers, structures you've probably seen without knowing what they were. Tall concrete or metal towers venting a faint mist. Inside those towers, warm water is deliberately exposed to air and allowed to evaporate. And here's the part that surprises most people. Evaporation is not a failure of the system, it is the system. When water evaporates, it carries an enormous amount of thermal energy away with it, more efficiently than almost any other passive cooling method available. That's why the towers exist, and that's why the water doesn't come back. It's not lost to leaks or waste. It is deliberately sacrificed to physics, converted from liquid to vapor, specifically because that conversion pulls heat out of the system efficiently and cheaply. So now, here's a question that might seem obvious, but actually isn't. Why not just recycle the water in a closed loop, the way your car's radiator does? The answer is that a car engine produces a tiny fraction of the heat that 10,000 servers produce simultaneously. And a closed loop without evaporation would require enormously more energy to reject that heat through radiators and refrigeration cycles instead. Evaporative cooling is not the fallback option, it's the cheap option. And at the scale data centers operate, cheap water is almost always less expensive than the additional electricity needed to avoid using it. This is where the story gets uncomfortable, because water is not an unlimited resource, and neither is electricity. And the two are now tied together in ways most people never think about. The reason isn't that data centers are wasteful by design. It's that heat removal at this scale has only a small handful of physical solutions, and the industry chose the one that trades a renewable-seeming resource, water, for lower energy costs and lower electricity draw. Which brings us to the real tension inside every one of these buildings. Cooling and computing are in constant competition for the same infrastructure budget, and every gallon of water saved usually costs you in electricity, and every kilowatt of electricity saved usually costs you in water. Engineers call this a resource trade-off, and it explains almost every design decision inside a modern facility, right down to where the building gets located in the first place. That's why data centers cluster near rivers, lakes, and reservoirs, not because the land is cheap, but because water access is treated as seriously as power access when choosing a site. A facility without a reliable water source simply cannot operate at full capacity during hot months because the alternative, pure mechanical refrigeration, draws so much additional electricity that it can undo the energy efficiency the entire facility was designed around. So the water and the electricity bill are, in a very real sense, the same bill, just denominated in two different currencies. Here's a fact that reframes the entire conversation. The actual servers themselves are becoming more efficient every generation, using less power per unit of computation than they did 5 years ago. But total water and energy consumption keeps rising anyway, because the volume of computation being demanded is growing faster than the efficiency gains can offset. Every video you stream, every photo backed up automatically, every AI model generating a response, adds load. The system isn't getting less efficient, it's getting asked to do dramatically more. And the growth curve for demand is currently steeper than the growth curve for efficiency. The interesting part is that some companies have started experimenting with alternatives. Closed-loop liquid cooling that touches the chips directly, air cooling designs optimized for cooler climates, or reusing the waste heat itself to warm nearby buildings instead of discarding it. These aren't universal solutions yet. They work in specific climates, specific budgets, specific regulatory environments, and they usually cost more upfront in equipment even when they save water long-term. That upfront cost is why evaporative cooling towers, the simplest and cheapest option, remain the default choice for most large-scale facilities built today. The building that stores your photos drinks as much water as a city of 50,000 people, and most of it simply evaporates. That's the sentence this whole explanation has been circling back to, because now you understand exactly why it's true. It isn't corporate carelessness. It's a direct, calculated consequence of thermodynamics colliding with economics. Removing heat from 10,000 densely packed servers requires either enormous amounts of electricity or enormous amounts of water, and right now, water is simply the cheaper physics to exploit. The reason this matters going forward isn't guilt about a single building's water bill. It's that the demand for computation, especially from artificial intelligence workloads that require far denser, far hotter server clusters than anything before them, is accelerating faster than water infrastructure was ever designed to support. Some regions are already seeing local strain on water tables near major data center campuses, prompting new designs, new regulations, and new engineering priorities aimed at reducing the water footprint without simply shifting the entire cost onto the electrical grid instead. What matters is recognizing that every digital convenience you use sits on top of a physical resource chain. The resource chain most people never see. Electricity generates heat, heat requires water, water requires local infrastructure, and infrastructure requires planning decisions made years before you ever click play on a video. The cloud isn't weightless. It's built from steel, water, and evaporating vapor drifting quietly off a cooling tower somewhere you've probably never noticed.